Good evening. Welcome to our, I believe now is our fourth webinar meeting between ACM Chicago and also IEEE Computer Society Chicago chapter. So we're very pleased to have you this evening. My name is Alvin Chin. I'm the chair of ACM Chicago, the chair of IEEE Computer Society Chicago, and also the chair of IEEE Chicago section. And tonight we have a very interesting and hopefully a very practical talk by Atul Dhingra of Standard AI. And he will be talking about navigating the complexity of ML production, insights, and lessons learned. So before we start, a huge thank you for our panelists. To ACM Chicago. So we have Mark Temkin, who's our vice chair, and we have our treasurer, Greg Newmark. I'm the chair of both ACM Chicago and IEEE Computer Society Chicago, and we also have, well, not on the line tonight, but our vice chair for IEEE Computer Society Chicago is Gina Martinez. You can see the URL of both of our websites. That you can go ahead and you can see our latest webinars, meetings, and even previous meetings too as well. All right, so tonight's presentation is from Atul Dhingra, and I will hand it over to Mark to introduce Atul.
Okay, hi everyone, thanks for coming. We have Atul Dhingra from Standard AI. He's, as you can see, he's in California. There's the Golden Gate Bridge right behind him. And he's going to give us his talk on navigating the complexity of ML production. So let's have a big internet round of applause for Atul.
All right. All right. So Atul, yeah, go ahead and you can share your screen. And while Atul is going to share his screen, for those who want to put questions, put your questions in the Q&A section, and we will gather those questions after Atul finishes his talk, and we'll address those questions afterwards. So put it in the Q&A and not the chat window. Thank you.
Good evening, everybody. I'm going to be talking today about navigating the complexities of ML production, insights, and lesson learned. A quick intro about myself. I am an engineering manager at Standard AI. I work on the problem of autonomous checkout that's powered by computer vision and AI. I have combined experience of over 10 years in industry and academia, and I've worked on various problems ranging from biometrics, autonomous vehicles, and autonomous checkout. So like just to throw you in the problem today, what I want to talk about is a very specific set of problems. The motivation I want to give you today is how do you sustainably scale your business in a domain where your data distribution is constantly changing across your deployment. So say, for example, you're in AV space, autonomous vehicle space, you're running your cars in Phoenix area, now you want to run them in SF, you want to run them in other cities. How do you sustainably scale your models or your business in cases where your input data distribution is changing constantly? So that's the thread I want you to hold on to, and I'll share what are the top challenges that we face here and some of the mitigation strategies there as well. So in industry, we typically, or at least in the problem of changing input distribution set, the top 5 challenges that I've seen in my personal industry experience is representative data distribution, second around scaling and deployment, third being around monitoring and observability, fourth on MLOps, and fifth on technical debt in machine learning. So just a caveat before we start, like you might have already understood, machine learning can't solve everything. You can't treat ML as a one-stop solution to all the problems. You need to understand if ML is the right approach for you. you need to verify if you can kind of solve your problem with a non-ML optimized solution before going to ML. And ML is very data centric. That's one of the key insights I'm going to provide to you today. And how do we kind of work around that? And with that comes the question, like, do you have enough high quality data points for your model approximation to learn? So you need to first understand if you can solve the problem in an ML way, and you have enough data points and enough high quality data points to do so. So the first challenge that I'm going to talk about is representative data distribution. This is one of the famous slides from a paper called Technical Debt in ML. And you see a lot of blocks here around what goes into serving a ML model. And you can see the small black box here, which represents the machine learning code, which we typically see as modeling work. And this is basically, in my opinion, less than 5% of what we do as a day-to-day in an ML org. There are a lot of other components around data, resource management, serving infrastructure, monitoring, and other tools around it that makes it ML serving possible. So first of all, let's start with data. Your data should be abundant, consistent, trusted, available, correct, and representative. So you might have heard of the first 5. I want to focus on the last point here, that quality of a good data is that data is representative. So what do I mean by data is representative? So your data set should accurately reflect the events and the behaviors of your model in real world, right? So if, for example, you're training an autonomous vehicle problem, like an object detection problem for your AV problem, you're trying to detect cars, is your data, input data, representative of what you will see at inference time? Like, are you capturing enough variance within the car sizes? Are you capturing enough variance within the level of illumination variances that might happen on a road, right? So I want to stress mostly on this last point, although all these different aspects kind of define what good data is. So the number one challenge that you see within data distribution is, how do you actually quantify the spread of your incoming data distribution? It's easier to do so at a smaller scale, where you can actually visually inspect your data and understand how your data looks like. If you're solving, say, the AV problem in a small region in Phoenix, you can actually look up your data and see how your data changes, but that becomes unfeasible as you scale up. And you need to have some direct metrics from your model and some indirect metrics capturing the impact of your model on any downstream consumer. So say, for example, again, the AV example, if you're training a semantic segmentation model for your AV, like route planning, what impact does a change in semantic segmentation model have on your drivable path or your control system on a downstream scale? And then finally, after a certain scale, you need specialized solution that allows you fast video, image, and feature indexing, search, and clustering. So the number one challenge at different level of scale is, how do you actually quantify the spread of your incoming data? The second challenge that we typically face is, okay, now I know, or I understand what my data distribution looks like. How do I identify the edge cases, or how do I identify the tail end distribution of my data? So this long tail problem is a very kind of known problem here, because in an AV example, again, how do you detect a person walking on a highway, which typically never happens when you do a data collection or when you're trying to train your model with any sort of standard data set? So how do you identify these edge cases? So you need to understand and test the set that captures the data distribution that is expected at inference time. So your test set should represent what you would be expecting at inference time. You should also be able to identify high uncertainty data points by leveraging human in the loop to label data where model fails in production. So say, for example, you saw an edge case of a person walking across the highway, which typically never happens. You should have an ability to identify these high uncertainty data points and be able to label them and feed them back to your model training. But the problem comes here is that capturing these edge cases is very domain specific. Say, for example, you're trying to create a drivable region model for your AV startup. How do you detect a brick or a person on a freeway, like I mentioned? How do you detect an airplane on a drivable road? You'll typically never see airplanes land on a road, but that's something that you need to be able to capture. And in these cases, at least your algorithm should be able to make some sort of safety stops, because at the end of the day, these are safety critical operations and lives are at stake. And you don't want to hit a person or hit any other person on the road. So what are the potential solutions here to this problem? Very simply, if you can actually enumerate your edge cases, data and labels can be synthesized or orchestrated. If you know you're expected to see, for example, a high variance of illumination on a road after a rainy day, you can orchestrate these kind of data collection and synthesize your data and labels from it so that your model can prepare to detect any objects in like high relief reflective surfaces from the roads. If you can identify model failures with domain-specific heuristics, you can iterate and improve on your model. Like I mentioned, illumination variance is one. Then if you understand if your model is generally bad on detecting trucks versus cars, you can have these model like domain-specific heuristics to kind of capture these production failures and make your models iteratively better throughout your production cycles. And you also need to kind of define accurately metrics and KPIs for your system to understand the impact of your tail end. So you actually need to understand all these data points that you're collecting that you say are edge are actually improving your overall metrics or KPIs that you care about. And you basically don't need to capture everything. You just need to capture enough data variance so that your model works as expected in production as what you're hoping when you train the model. Another strategy is to start leveraging or leverage human in the loop to kind of tag production failures. So that's typically how ChatGPT was earlier trained. Like people that used to give an output and people used to, like all the people who were looking at the outputs, we used to say, okay, this is wrong, this is right. And you can then basically capture or leverage human in the loop to tag these kind of production failures that you might see. And human in the loop is kind of inevitable part of ML in production. You need to understand your model does what it is supposed to do in production, and you need to have some sort of a human in the loop element, although that kind of diminishes as you go forward. And then at the last, I think there's also a big market coming up for specialized databases and feature stores that allow you to store, index, and cluster your data. So you can slice and dice your data and try to understand what your data distribution looks like, what are the tail end distributions for your incoming data. Good. So the second prong that we typically face is around scaling deployments. And when I say scale means different things at different levels. So there is typically scale of going from 0 to 1, where you're trying to basically move fast and break things. You're in a POC kind of a stage. You're trying to build a new thing to showcase that you're able to solve a problem effectively. From 1 to 10, you show an ability to scale just outside of a single isolated use case. Like, can you deploy the AV that is running in Phoenix and train there and be able to run it in like a road on SF, right? And then the final part is the actual scaling that I typically refer to as scaling, is from 10 to 10,000, where can you show sustainable growth and stop bleeding money or make profit while you're doing that? So these are the problems at different deployment strategies change with level of scale that you're thinking of. So typically, you want to understand how your cost is decomposed while you're thinking about scaling. What are your fixed costs? What are your variable costs? and how can you reduce these fixed and variable costs. So for example, fixed cost could be your hardware cost or your GPU cost. Variable cost could be any sort of operationalization costs that you come across. How can you fix hardware costs? Maybe you choose a better hardware. How can you reduce variable cost? You basically make your operations much more leaner by capturing any sort of tail end distribution that you are seeing, so as to kind of overall reduce the kind of failures that you're seeing, so that your model is now in a kind of self-learning loop of where it identifies where it fails and kind of relearns on those kind of failures that are happening in production time. And then you also need to understand your product roadmap requirements from inference versus accuracy, like what is more important to you. Maybe if you're going in an AV industry, your accuracy matters to you more because it's a safety critical operation. You don't want to like hit any person on the road, versus any other operation. For example, you're serving cats versus dogs as a product, then at that time your inference matters more, although accuracy as well. So you need to understand these trade-offs for your system. The third problem that we typically face is around monitoring and observability. So let me kind of give you a brief overview of what we think about as monitoring. So there's this famous quote by Ben Franklin, is by failing to prepare, you're preparing to fail. So you should be able to monitor what's happening in your systems. It should expect to work in the same way at inference time, what you're expected to get the outputs from at training time. So monitoring models in production is an important aspect to ensure that your model is doing what we expect it to do in production. And within monitoring, specifically in an ML system, there are three main components. If you think about typical software design, you will look at model and configs as the only thing that you kind of care about, going from one iteration to the other. But within an ML system, you care about mostly three things, where you care about the code and the corresponding config that defines your ML system. You also care about the model that is generated out of your ML system. And thirdly, you also care about the data provenance or the data itself that is used to train the model it's generating. So if you miss any of these three components, you won't be able to kind of backtrace any kind of issues that happen in an ML system. So these three components are required to build an effective monitoring loop in an ML system. And without a way to understand or track these data changes, hence the model changes, you cannot understand how your model performs or how your model degrades overall. So monitoring is typically hard. There's this famous, again, I think I'm probably referring the same paper on technical debt. There's a problem on entanglement where it poses a problem of changing anything changes everything. So if you're changing, say, for example, a model config for your, let's take a simple example of an AV domain where you're trying to detect semantic segmentation map of your road. If you have a two-stage system where you're detecting objects on the road and then building out a semantic map after the fact, if you make any changes to your object detection model, all the subsequent or downstream consumers of that model will get impacted. So any changes to your object detection model can have a drastic impact on your semantic segmentation models as well. So there's this component of entanglement within an ML system that cannot always be decoupled, where an upstream model impacts a downstream model, and any changes to the upstream model can have drastic impacts on the downstream model as well. So typically in like changing any distribution or any input influences all the outputs. Adding or removing any feature changes model output distribution, and your retraining become not reproducible. So any configuration parameter is just coupled. So any sort of change in learning settings or hyperparameters cause a downstream effect that cannot be traced back unless you're able to decouple these configs. The other kind of component which makes monitoring hard is around configuration. So because model hyperparameters, versions, and features are controlled in a system config, any changes or any slightest error that you're not maintaining your configs effectively will have a drastic impact on your software, on your ML software, right? This is specifically true where models are completely and constantly iterated over and they're changed very minorly. Like if you're releasing your models every week or every other week and you're maintaining your configs in some system, any changes or any kind of lapse or error there will have a kind of catastrophic effect of not being able to backtrace any potential production failures or model failures that happen in your system. So why do we need monitoring? We need monitoring to understand the data skews. So what our training data and what our inference data look like. So typically your training data should be representative of what you're expected to see at inference time. But if not, you need to be able to monitor for that. You need to monitor for any sort of model degradations that can happen. This can happen due to a lot of things, like it could happen due to any data shifts that happen in your environment or your consumer behavior or any sort of adversarial scenario. So for example, if typically you're running your AV car in a Texas environment and you never see snow there, but all of a sudden there's like a snowfall, your data has changed, your car or your vehicle doesn't know how to react to that, or your model does not know how to react to that. So if you monitor your model degradation due to data shifts or model shifts, you can address those going forward. And model degradations can also happen due to any sort of adversarial scenarios. So very famously, I think there was a example around where a stop sign was changed by a few pixels and the AV vehicle, I think it was a Tesla, if I remember correctly, was not able to detect that sign. So these model degradations can happen either due to general shifts in data or some sort of adversarial component. You also need to be able to monitor any sort of negative feedback loops. And this is, I think, one of the most critical points here. You do not want, although you want to build out feedback loops for your system, you do not want to introduce any sort of negative feedback loops in your system. So by negative feedback loop, what I mean is that when your models are automatically trained on the data collected in production, if you're reusing the data that's being generated by a model and reusing that data to retrain your model, you're building out a negative feedback loop. And that's typically what you see in recommender systems. So any sort of recommender system can go astray if you feed it, if the user feeds it enough garbage data, right? And this happens in traditionally all ML algorithms. So this is one of the more important points to be aware of when you are building out these monitoring systems, to have a way of understanding or capturing these negative feedback loops that exist. So what do we typically want to monitor? There are a few components that you want to look at. You want to look at operations monitoring. What is your latency, IO, uptime of your models? Are they changing? Is that within the expected mean, median variance that you have and within the tolerance that you have? Is the model that has experienced any sort of slow leak regression in training speeds or serving latencies, throughputs? So you want to also understand the model performance and any sort of regressions that happen. You also want to monitor your predictions, right? Is the expected min-max ranges or the standard deviations of your output predictions within the range that you expected, or something drastic happening? You also want to monitor any sort of config or dependency changing that impacts your model directly or indirectly. You would also subsequently also want to monitor at the end, in the production side of things, what your training and serving skew looks like. So at training time versus serving time, what does your feature set look like on the same values, right? So it should generate a similar value if the expected serving skew is similar to what your training skew looks like. You also want to monitor that models are not too degraded, either due to model drift or data drift, and model has not experienced a regression in prediction quality on served data. And lastly, you'll also want to monitor your inputs. What if your input sensor is faulty? If you're a vision only AV company, and if there's any damages to your input sensor, then any subsequent predictions that you make on top of that will be impacted. So you also want to monitor how your input to the model is changing. And of course, you want to capture any model and data versioning and want to make sure there's a clean lineage for model and data and code for all the releases that you have. So I've picked up a few things from this Grafana website where they talk about observability, testing, and monitoring. What I want to focus on is this particular slide, which I'll go through next. But observability is the key way how you describe the event context and reduce the data into something useful. And there are basically 3 pillars of observability. What are the metrics generating from your system? What are the logs? And what are the distributed traces? What all systems did your model or your inference hit while you made a final output, right? So if you're going through a cascaded model structure of going through object detection, semantic segmentation, drivable space, can you actually have distributed traces in all these 3 components to understand where, if any sort of degradation happens, be able to find and pinpoint where the degradation and what the source of that degradation is. And testing is basically our best effort of verification of correctness, and monitoring is our best effort to track predictable failures. So in this observable space, there are some events that you can test for, some that you can monitor. This overlap is what you want to simulate all sort of failure boards to build out a good set of unit tests and regression tests. The fourth and fifth problem I'm going to talk a little bit briefly about, but fourth problem that we typically see is around MLOps. And this is something that you might have started to hear a little bit more in the recent times. MLOps is machine learning operations. So it's basically, rather than ship and forget pattern, like in a traditional software, in machine learning system, you require iteration and loops and continuous improvement. So that's what MLOps structure is made around. So think about ML as a continuous delivery mechanism where once you build your model, evaluate it, productionize it, test it, deploy it, you are able to monitor and observe any sort of degradations that happen and be able to capture them back so that it becomes now a loop that is able to deliver you a continuous delivery for the ML model instead of just publishing or deploying a model once and then forgetting about it. And typically you see, like I mentioned, we want to version code, model, and data at these various points in time. But the point I want to highlight here is this is a continuous system of delivery where there's a kind of continuous loop or a feedback coming in from your observability part of the stack. So if this is clear, there's like a few complexities that we typically see in day-to-day. One of which is that we work with complex infrastructure. So you need to have diverse support for different kind of infrastructure that you're supporting. Maybe you're training a model on a GPU, maybe you're deploying it on an ASIC or a TPU. So you need to have these diverse environments and be able to support these, not just infrastructure, but also the libraries and frameworks around these different hardwares. You have multiple steps in a ML workflow. So you need to understand the requirements of, okay, when do you need a high compute for training or high bandwidth for data ingestion, or what kind of hardware do you need for inferences, like a low compute or a low power. So there are different steps in an ML workflow which define or describe what kind of infrastructure that you're going to use to build that. So there's a lot of diversity and complexity to the infrastructure that you need to maintain. Model lifecycle management. So again, unlike software development, you have to go through this continuous deployment strategy. And traceability of model and data becomes imperative that we touched upon in observability slides a few slides back. And then you also need to have compliance with your current operations. You can't completely introduce, or you can't introduce a completely new workflow for your DevOps teams. You have to be consistent across a company. You can't be building your software stack in 10 different languages or 10 different frameworks. And then this organization adaptation kind of stems from the same point, is you need to then understand that ML teams and hardware SRE DevOps teams now have this shared responsibility of developing this, not just the infrastructure, but the overall delivery mechanism of this ML software. The fifth challenge that I want to touch upon is around technical debt. So technical debt, to summarize, is the long-term cost of moving quickly. It's similar to fiscal debt, and there's a good reason to take it, but it needs to be repaid. And unpaid debt compounds quickly. There are a few causes for technical debt. Lack of tests. Your system is too complex. You're writing some sort of spaghetti code. You have many dependencies and entanglement within your code base. Your code has poor readability. You have design anti-patterns, or some sort of, basically this happens always, uncanny correlation with deadline pressures. So what are design anti-patterns? Glue code is one you might have heard of. Okay, putting things together in an in an ad hoc system and making things work. This creates sort of pipeline jungles where you're using code bases in different languages or different kind of libraries or frameworks, and this creates these jungles that cannot be untangled easily. There's this very famous example of Knight Capital losing about 400 million and like 45 million in 45 minutes. They were a stock trading company. They had some dead code base in their system, and it made some automatic buys and sells and cost them like almost 500 million in 45 minutes before they could catch what kind of dead experimental code was doing that. And you need to be able to understand if there are any bad smells in your data or in your languages or any prototypes that you have. I think I touched upon this a little bit briefly, but CACE is changing, and anything changes everything. And it's not typically possible to make isolated changes. And this applies to features, signals, parameters. So you change any sort of feature or a parameter or a config, it's going to have downstream impacts of changing everything. And typically this happens more in the cases where you have a dependence or a cascade of models. So if your model A or a system A depends on system B and system C, if you're feeding in an output from A to B and B to C, any changes in A will have a cascading effect on B and C as well. Right, and the mitigation here is basically you want to have at least learn the corrections or learn the connections between your models and interfaces and be able to detect these cascading outputs and account for those. So some general mitigations here is be aware of the technical debt. You can't get rid of it, but at least be aware of what the debt is. And you want to continuously test for this debt. You want to measure the impact of any new changes that you make to a system. And you need to understand how quickly can you make a new team member onboarded with any sort of code base. If it takes you a week to onboard somebody, then you have too much technical debt, right? And you want to also pay per model. You want to be in a practice of, okay, I want to take on this technical debt now, but I'm going to pay this as I kind of get to closer to a deployment cycle. Because if you do not pay per model, it kind of combines and it kind of becomes a nightmare. So you want to, in that way, prune experimental code paths. You want to monitor and map all your consumers and all your inputs to your models and make sure you have enough testing around those. And you also want to have some sort of configuration testing that versions your configs and you also want to understand what your data dependency is. It should be, again, very versioned, comprehensible, and testable as well. And there's this famous ML test rubric paper. I think this is in the reference section as well, but it gives you kind of a way for you to test your current code base. It's a good exercise to understand where you stand. Would recommend people to take a look at this. So yeah, those are the typically like 5 challenges that I've seen in my time so far in the industry, and that's pretty much it. I would like to put some questions in now.
All right, great. Thank you, Atul. So we have, we have quite a bit of time for our questions. So are there any questions from the audience we have here? Okay, well, maybe let me, first of all, maybe I'll start with something and then other questions will come trickling in. So with what you just mentioned about, so what is it that in terms of how Standard AI, the company you're working in, how are you implementing or how are you taking these things, when you are going and deploying your particular models? Do you have particular, tools or so that you're using to be able to, do this kind of, machine learning operations? Are there any, kind of like some rules of thumb, to follow, when you are doing the deployment, special things that you should be checking for, something like that?
Right. So can't go into much detail on the specifics, but typically it's a mixture of industry available resources. If there exists a solution that solved a problem that you want to solve for, you want to buy that resource, there again are going to be very specific problems to your use case. For example, like in an AV industry, it's very critical that you identify any sort of drivable path, right? You don't want to hit anything on the road. Those kind of custom solutions typically are built in-house. So there's a mix of buying versus making, and it totally depends on the scale of your operations as well. If you're, again, in the scale of going from 1 to 10, you typically won't care about much of these things because half of the things that you work on may not even end up in a final kind of production solution. But when you think about scaling, like going from like 10 to 10,000 kind of a scale, that's when you start to kind of highlight or identify these top things that's taking your engineers' time away. So that's typically how you prioritize for it and try to find either an external solution or build some solutions in-house around model data. Sorry, it's a little vague, but it kind of comes in by evaluating how much time, hands-on time, that you are spending on something that can be automated away, right? So that's what my rule of thumb is.
Okay. So we have another question here, kind of a little bit on similar on what I had mentioned about. Do you have a recommended machine learning pipeline?
So yeah, again, depends on the use case. So for example, if you're building out something very new, you would want to leverage kind of cloud resources, for example, versus when you're trying to scale and you think about your costs of deployment, you want to build out or you want to leverage some sort of edge platforms to deliver or deploy these things. So again, it kind of depends on what stage of the problem that you're trying to solve for. I don't think there's a clear answer, but typically the journey that people take in most of the industries is you start out with a solution to a problem in a more hacky way, using or disregarding what are the usages and consumptions of the resources. So you buy things out, and after a while you try to figure out, okay, this is my max expenditure on this tool, which I can build out in-house at half the price, and then you start to transition over. So there are, again, I would recommend looking at different components or different tools in the area that you care about. For example, if you want to look at, okay, how do I serve the model? Like there are tools from GCP, there are tools from AWS, right? You can use Vertex, you can use similar tools from AWS, versus now when you're at a stage of, okay, I can't afford to incur so much cost from GCP or the AWS, then you think about, okay, maybe an edge solution is better for me. Maybe let me think about what is the cost of putting in like that initial fixed money and then seeing how much it lasts me. Like if your typical hardware breaks in like 4 years, what is that return on investment? So I think that's typically how you think about it for tools as well, is what stage of scaling you're thinking about. And easiest to going from the easiest solution and then trying to figure out what is the thing that's costing you the most or costing you in terms of dollars or in terms of time, that then you try to solve for specific solutions with.
Okay, we have a question from Greg. Greg.
Yeah, one thing that caught my eye was when you're talking about the negative feedback loop, where your production data goes back into your training data, and that can cause problems. And I'm thinking of course, things like ChatGPT and people talking about certain iterations or certain companies' use of that. They are just restarting the conversation every time, and other ones apparently are storing all the conversations and using that as additional training data. And with your comment there, it seems like that is potentially risky. Like it's a different set of training data when you're interacting with an AI versus scraping the web and just taking normal unobserved, or people didn't know they were being observed by an AI and using that as the basis of your training.
Right. So like a very insightful example here would be, say, for example, I as a user write a blog post with the help of ChatGPT and I publish onto my website. And a month down the line, ChatGPT references the same article to provide more insights on top of it. So if I cannot verify the output from ChatGPT at that point, and in a later subsequent version, ChatGPT actually uses that as an input to generate more analytics on top of it. This is what negative feedback loop is, right? So you are using an output from a system as the input of the same system, which you do not know is the right output or not, right? So that's kind of one way of thinking about this.
Okay, thank you, Greg. So another question we have here is from David. And regarding about, do you spend much time on machine learning understandability? So I guess I think what he's probably referring to, I guess, is like, everybody may have heard about, machine learning, like explainable AI, right? So I know that Stanford is doing, a lot of work in explainable AI. I think with Fei Li, right, who's a professor, there, a famous professor there. Can you maybe spend some couple of minutes talking about that?
Right. So it kind of again depends on the domain. So for my use case, like my work use case, I do not spend too much time on explainability because the kind of problems that I'm trying to solve for is in autonomous checkout, for example, is where are people in the store? Like you want to detect their 2D estimates and 3D estimates in position, and what are the carts? So what are the virtual carts those people have? So explainability isn't really as useful there, because at the end of the day, what you care about is you're not using any PII information from the people, but at the same time delivering value to the customer. Whereas in other domains, which this becomes a little bit more important, is, say, for example, medical domain, right? Are you using an output from, say, like a generative model or an ACM or something to order your patient care, for example? And how are you doing that? Like if you're putting or ordering your patient care based on some input to your model, can you explain why you did it? Or if you're saying this person based on an X-ray has a fracture, or this person has a cancer based on some sort of a scan, can you explain what you saw? Because that is more important to understand context with. So to answer your question, I don't do that too much within my job, but I do that like on my own time. I think to think about these problems, I think it's more critical where both ML and humans are working hand to hand. that's where explainability is more useful than if you're building things autonomous end to end.
Atul, some more questions. Can we do this on a phone? No, just kidding. Do you work on PCs, and what kind of PC would that be? How high powered is it? Or do you have to work on high performance computing systems with cloud-based resources?
Right. So if you're training any sort of deep neural network, you typically require a GPU-enabled machine to do so. If you're working on algorithms that don't really require that, but you require a lot of kind of compute in terms of CPU cycles, you use high memory CPUs for those. So it depends on what your use case is. And use cases typically change going from training to deployment as well. So we would typically train on a much bigger instance of a GPU cluster and at inference time, we will try to use that kind of makes the inference kind of cost effective, right? So even within the same stack, what problem that you're trying to solve for impacts what kind of systems that you use.
You may know about back in the 1980s and 90s, there was this real push toward AI, and eventually it turned into what people call the AI winter. Is it possible that with the push we've had for the last 10 years with ML and AI, that this situation could occur again, that we found out that we were all wrong and we were chasing after the wrong solution?
Could be. I don't think there's a definite answer here, but the kind of pace of changes that I've seen, especially like with this recent buzz with ChatGPT, it does seem unlikely for a bit. And it's also the amount of problems that we are able to solve. I think originally, like in 2011 timeframes or 2010, when the ImageNet paper came out, it was mostly ML or like deep learning was mostly trying to solve vision problems. Now it's expanded its scope to language models and NLP, these kind of things. So I don't think that is going to happen soon. But yeah, we could be wrong about how we are creating these models, but I think the outputs that we are getting from it don't really say so.
Okay. Here's two questions I'm going to combine together about risks. Do you, I think meaning your company, or companies like yours, do they have to take out any business liability insurance for their ML products? And do ML products inherently have higher risks than traditional software offerings?
To be honest, I don't think I am the right person to answer that, but I can give you an educated guess. I think there is definitely an added liability of data that does not exist in software. So you need to be able to capture the variability or the kind of, you need to manage data well, is what I will say. So there is like all this GDPR concerns about, are you sharing any personally identifiable information or not? So there is definitely an added element with ML systems as compared to software. But overall, I don't know. I don't think I'm an expert there, but that's my take on it. There's added component there, or added layer with data.
Okay. Let's see. Let's ask this question. And when you have a trained system, is there a general ratio between the size of the training data versus the size of the neural network?
Typically not. How you typically train a neural network is you try to create a model or a neural net based on the representation of your input data. So say, for example, you're trying to solve for object detection, you're trying to detect cars versus trucks. So that amount of information can be learned with a model of a specific size versus you're trying to do not just object detection, but semantic segmentation or doing some more kind of cascaded things. Then you need to have much more capacity of your model to learn those nuances. So it's not about the size of the data, it's about the variance within the data. And it's about the variance of your expected output classes that impact the kind of model capacity that your neural network needs to have.
And we'll end with this question. What trends do you see in upcoming machine learning tools?
Yeah, I think definitely there is going to be, in my opinion, going to be like a huge push in the direction of being able to index and store your data and metadata effectively. I think data ops, which is kind of part of ML ops, is going to be one of the critical components, because as you realize, data is the most important part. And if you are able to appropriately capture the right kind of data points that your model needs to learn or your model needs to train on, that is going to make your ML systems much better in the longer run than trying to feed it 1 billion points. So 1,000 good points is much better than 1 million bad points, is what I'm going to say. And I think this push around how you store, index this data and the metadata around it is going to be pretty useful in the next, I guess, like 5 years. I think there are like a lot of startups doing this, but having that solution and having a solution that works well is going to be the upcoming trend. So a lot around ML ops, but I think more on the data side of ML ops.
Great. Is it possible for people with a standard computer education, but without being any specialization in machine learning or AI, do they have a path forward into that area of the industry?
Yeah, I think there are enough resources online to do so. I don't think, I mean, of course, education is important, but I don't think that's a limiting factor. There are unlimited resources for you to learn this within the resources that you have. And there's a lot of online courses or project works that you can start taking up to build that understanding and build that expertise in that area without going through proper university education.
Great. Well, thanks a lot, Atul. Thanks for your presentation and answering all these questions. So thank you for coming to our presentation. We have presentations generally once every month, except for July and August. And sometimes we sneak a July presentation in. And we always look for speakers. And maybe one of those speakers or several of those speakers could be you. And that's why we're open to anything that has a computer in it. If your topic is interesting and you want to speak about it, and it's got that one minimal connection, well, you're a candidate to be a speaker. And I think it's a really good opportunity. We are going to have in-person meetings in Chicago at a certain point. We're definitely making a plan for that. So if you are in the area, that's also a possibility, a in-person talk. And let's move on to the next slide. But looking ahead, I just found out about this during the meeting itself. This fall, we're going to have Jacob Gaburi. I hope I'm enunciating his name correctly. He's a professor at University of California, and he just wrote this award-winning book called Image Objects, which is the basically history of computer graphics, especially the earlier period, not the most early, but the earliest periods that documents what took place at University of Utah and onwards. And he's been a speaker at SIGGRAPH a number of times, and we just wrote him and asked him if he would be interested giving a talk to us, and he said yes. So that's going to happen sometime this fall. probably not October, but a month before after that. Okay, and also we have videos. If you've missed any of our presentations or want to watch them again, go to bit.ly ACM Chai video. And we don't have up there was some of our most popular videos are ones given this year on the metaverse, definitely the end of programming, and the Davos talk that took place last month. So go visit our YouTube video site and see the presentations you might have missed or want to watch again. They're ready there for you to see. And we're always looking for volunteers. This doesn't happen without activities happening on in the background that you don't see. And so these are all great skills that you could learn if these are things you haven't, that will help you with your job. And we have opportunities for writing, planning, working on the video aspect, and finding new speakers and topics and helping build interest in computing. So again, we're looking for speakers and topics. That could be you. You can contact me at vice chair at chicagoacm.org and Alvin at chair at chicagoacm.org, and give us your ideas and tell us about yourselves, and we'd be happy to present to you. So thanks everyone for coming tonight. Thanks Atul for giving your talk, and thanks for everyone for your questions. So we'll see you next month.
URL for the YouTube videos, if you just go to bit.ly/ACMCHI video, you should be able to find the, yes, right there, right, bit.ly/ACM Chai video. Just leave it there on the screen if people want to capture that. So you can see our previous videos there. And also before we end, I just want to make a note of that. If you guys need to have a professional development hour certificate, this counts as one. So if you need that for your professional engineering, then you can get that. We will post that onto our site or so you can be able to download it and you can claim that for professional development hours. This meeting was recorded, so you'll receive a recording of this webinar as long as with our slides and Atul's slides. And so with that, yeah, thank you. Like Mark said, thank you everyone for joining this evening. And we'll see you in our next events. So take care, stay safe, stay healthy, and we'll talk to you soon then, and have a great evening.